Descartes' theorem is a way of deciding how many roots you're going to have and what those roots are going to be based on positive, negative, or imaginary, and their total. So the number of positive real roots is going to be based on the number of sign changes in p of x. And that's our positive p of x. Then the number of negative real roots is going to be based on the number of sign changes of p of negative x. Odd exponents are always going to change in p of negative x, and the number will decrease in pairs unless there's only one, because you can't take anything away from one. You can't take a pair away from one. Okay, so that might not mean a lot, but let's look at an example of this. So first thing we're going to do is we're going to start with our zeros and our total zeros. Our total zeros is how many roots is this going to have? Well, it's going to have 4, because that's our highest exponent. Then we can go over to the zeros column and we look at our original problem and say, is there a greatest common factor equal to x? Is there an x that we can take out of every single term? And in this case, there's not. So that's going to be 0. Okay, so here's where the p of x and the negative p of x come in. We're going to look at the equation. This is positive x to the 4th, negative 5x to the 3rd, positive squared, negative, positive. So we're looking for how many times does that change. So from positive to negative is 1, negative to positive 2, 3, and 4. So there could be 4 real roots. So up above we said it'll decrease by pairs. So if you have 4 and you take away a pair, you're down to 2. If you have 2 and you take away a pair, you're down to 0. So you're going to keep subtracting those in pairs until you're down to either 0 or 1. So then here's where the negative roots come in. Okay, so I would go up and I would circle everything raised to an odd exponent. Because here's what's going to happen. Odd exponents will change sign. Okay, odd exponents will change the sign. So this one was negative, so it's going to become a plus. This one was negative. It's going to become a plus. So all of the ones that are even are going to stay. So plus, plus, and plus. So all the way across here, you have plus signs. So how many changes are there? There's none. There's 0 roots. Okay, so what we're doing is we're looking all the way across. So like this would be row 1. In row 1, what do we need to add up to 4? 0, because we have 0, 4, 0, 0. This is row 2. 0, 2, 0. We need 2 more to add up to 4. This is row 3. 0, 0, 0, and 4. Okay, so what's the point of this? Well, the point of this is so now we know when you're checking your P's and Q's that there's not going to be a single negative. So if you had 48 different options for P's and Q's and half of them are negative, you've now made it down to 24. Okay, so you don't want to check any of those negative ones based on that. So let's look at another one. Okay, so first, how many roots? How many zeros? There should be 5 because it's our highest exponent. Is there a greatest common factor of x? Yes, I can take out 1x from all of those. So we would take out a 1. Okay, so now let's look at how this goes. P of x, it's positive 5x. Then it's negative. Then it's positive again. So there's 1, 2 sign changes. So I could have 2, or I could take away a pair and have 0. And I can't take away any more than that, so we stay at 0. So now let's look at the negatives. I'm going to circle all of my raised to the odd power. All of these are raised to the odd because technically that's raised to the first. So this one was positive, now it's negative. This one was negative, now it's positive. This one was positive, now it's negative. So it goes negative, positive, negative. 1 change, 2 change. So I would have 2, take away a pair is 0, and 0. So then the imaginary roots are filling in the gap. So if this is line 1, we need these 4 numbers to add up to 5. Well, they already do without anything, so this would be 0. Line 2, we would need 4 here. This one would also need 4, but this is just a repeating row, so we really didn't need this. So let's look at what that means in terms of the graphs. So maybe the whole point of this is to see where you would have roots at. Okay, so I know I have one that goes here. So it might look something like that, where your positive roots are here and here, your negative roots are these two, and your x is this one. Whereas the bottom one, number 2, you're going to have 4 imaginary roots. So maybe it looks something like this. I guess I probably need to curve one more time. So this is the only root you would have. The rest would all be imaginary. So that's the point of this, and to help narrow down your P's and Q's when you have a whole bunch of them that aren't quite as nice as the ones that we've been doing.